So I've noticed most people do not have mechanical engineering design experience, and this can be quite a limitation when you're working on a car. Um, Now, it's all very well to have practical experience because rule of thumb work is actually some of the best way of doing things. If people notice it's something that works by experience, then they can simply go and replicate that, and that's how most people who tinker in their garage operate. But I thought it would be interesting and useful to just explain how the industry actually does things. They do not do this trial and error process to the degree that a home mechanic would do. They do actual design, and they employ mechanical engineering design principles. And if you study mechanical engineering, you do a subject called mechanical engineering design. And I'm going to explain exactly what this is and exactly how mechanical engineering components get designed, and how this can actually be useful to you, and where to look this up. And if you have the mathematical background, how you can actually do calculations to make sure that you make things that don't break or correctly fitted or whatever the case may be. One of the standard texts for mechanical engineering design is this book by Shigley, which is a book familiar to most mechanical engineering students. There are other textbooks. This is an older text, so they may not know this, but for many mechanical engineers, they'll be intimately familiar with this book. It's a handbook of mechanical engineering design, and it contains almost every kind of design of almost every kind of mechanical element. So I'll just show you what's in it to give you an idea of what this is about, and then I'll show you specifically how this pertains to the axle that I'm making. So it begins basically with stress analysis. Stress analysis analyzing the failure of materials. It then goes on to deflection and stiffness. This is not a particularly important chapter. Statistics, this is failure modes and so on. Static analysis for building trusses and things like that. Beams, columns and that sort of thing. Fatigue failure is very important for designing critical elements that may fail for fatigue so that they survive their useful life. Screws, fasteners, welds, springs, and this includes many different kinds of springs. Rolling contact bearings. This has got things like, for example, stress distribution at a contact point on a roller bearing. Journal bearings is a big area because this involves fluid mechanic analysis of journals to make sure that they're just the right thickness. Gears, other kinds of gears, shafts, mostly things like torsion and so on. Clutches, brakes, and flexible mechanical elements like belts and so on. So we'll see how some of this works. So this is, for example, deflection and stiffness considerations, an example chapter. So you can see the sort of analysis they do. They take an idealized beam with a force on it and work out the deflection distribution and so on. There's a lot of mathematical analysis. And then they always conclude with an equation that you can use. And you can see it's very mathematical, and a lot of it would be quite difficult to follow if they didn't have very nice examples. So here they give an example of analysis of a beam, for instance. At the end of each chapter, there are also lots of exercises that you can carry out to test your skill, and I think there's even a book of solutions to all these problems. Here, for example, is a a spring and a fastener, and there's some kind of question involving analysis of this component, stress, tension, compression, breakage, and so on. And some of the questions would be, for example, things like design this so that this thickness is correct, or that the spring will not fail, and so on. Here is the design of a gear, and there's a whole analysis goes into gear geometry. You can see the sort of analysis they do and the sort of problems they have. Now, the intention of this book is that you have all the mathematical tools to design something and not have to experiment. The reason why you experiment after you've done your design is to test that your design is correct. But your design ostensibly ought to be correct. You're just double checking by doing your experiment. And your experiment may fail, but you're not doing an experiment as a trial and error mechanism to work out if your design is correct. You're doing the experiment to validate that you've made correct calculations. But ultimately, what you intended, the intention here is that you design everything on paper. If you can't design it on paper, which is extremely rare, then you'll go and design it using a finite element model on a computer. But most elements, certainly in something like a automotive vehicle, can be designed on paper. In fact, they can be designed with a slide rule. So a good example of this is the critical frequency of helical springs. So this is what happens when you get spring surge. Now, you can actually do calculations to make sure this doesn't happen. You don't need to experiment. You can use the equations in this book to make sure that you don't get spring surge. So often people will complain that parts in a car are over-designed or that they're under-stressed. So people will say, well, you know, this particular component can actually handle a lot more load or a lot more something than the manufacturer intended. So what happens is they'll take an engine that's designed for a certain compression and they'll use a turbocharger, and they'll say things like, well, this engine works fine with double the horsepower. So from the manufacturer's point of view, they want to make sure that they get no recalls on the engine. And statistically, they can predict that a certain piece of metal, when it's got a certain stress on it, that the variation in the field is going to cause them to have so many recalls. And that's why they understress and they over-design all the components to a degree that it's extremely unlikely that that component will fail in the field. So when you see a crankshaft and it's a certain size and the horsepower rating is such and such, it's because that's what the manufacturer knows won't break. And it won't break to a statistical certainty. If they get 1 in 1,000 crankshafts breaking in the field, that would be a complete disaster for that particular model of vehicle. Now, on rare occasions, so they are not actually over-designing anything. They are trying to design things to the absolute limit to save every possible cent on the price of a component. Now, in some cases, there's no manufacturing process available to make things to that limit, and things will be over-designed. That does happen sometimes. I mean, just off the top of my head, the Nissan Skyline 6-cylinder crankshaft is a forged crankshaft, which is much stronger than it needs to be. Why that is probably has to do with an industrial engineering decision, not a mechanical engineering design decision. But ostensibly, every single component is designed to be just short of failure over the life of the vehicle, and by this we mean the warranty period. And of course, maybe the life of the vehicle will be specified longer if the manufacturer wants to have a good name in the industry. So things do last a long time. So that is how everything is designed. And I can't think of any way. I mean, I've never worked in automotive industry, but I can't think of any other way that you would do it. And certainly when you're taught in mechanical engineering, this is how you are explained how you should operate when you become a mechanical engineer. You do things within certain parameters, and you never ever exceed those parameters because of the statistical possibility of a failure. So now we're actually going to apply a proper design principle to the axle shaft. And what we're going to do is we're going to find the appropriate section in this book. I looked it up in the index, and this is basically press fits and interference fits. They're called interference fits because something smaller, some hole which is smaller is fitting over a shaft that's larger. And both go through a very slight deformation. Not a permanent deformation, but a very slight deformation in order to fit with each other. And there's several reasons why you do this. So the section that I found in the index is this section, and I've read through this, and this doesn't require very much mathematics to actually understand. It's just basically a bunch of lookup tables. So fortunately, there's no calculation involved because there's a standard in the industry about how you actually do this. And if you look for the different types of clearance, they've got an outright clearance where the shaft is actually smaller than the hole, a loose running fit, a free running fit, a close running fit, a sliding fit, and a locational clearance fit, which is a very, very snug fit. So this is for things that are stationary, but you can assemble them and disassemble them without a press. And then you have what's called the transition area, where you have things that you have to actually be pressed together or heated up so that they can fit together. And these would be things like bearings and so on. And I think the axle tubes inside the pumpkin is an example of this. A locational transition fit is for accurate location, a compromise between clearance and interference. And then you have a locational transition fit for more accurate location where greater interference is permissible. And you can go one tighter where it says a location interference fit for parts requiring rigidity and alignment with prime accuracy of locations but without special bore pressure requirements. That sounds actually what we need. And then you have a medium drive fit for ordinary steel parts or shrunk fit parts on light sections, the tightest fit usable with cast iron. That might be a bit too tight for what we use because we actually do have cast iron. And then a force fit suitable for parts which can be slightly stressed, or for shrink fit parts where heavy pressing forces required are impractical. So this is where you really have to heat things up, where it's a big part, you can't even press it together. I'm not sure where the piston pin inside the eye of the rod, connecting rod, would come in this. This is actually sounding really good. This light interference fit here, called a location interference. So let's go and look up what the tolerances are for this. Now, according to this discussion, you've got to take this figure here and go and look it up in a table in the index. So in the index, we have table A14, selection of international tolerances or grades, fundamental deviation for shafts. So these are standards. Like I said, you don't calculate this, you just look it up. So let's say we want to do this one, location interference fit, but not the largest that can be used for cast iron, without special bore pressure requirements. And I don't think we need bore pressure. It says H7P6. So H7 means that we go to the IT7 column, and we're dealing with something between 50 and 80 millimeters, 63 millimeters, which is 2.5 inches. And it says here 0.030 millimeters. And 0.030 millimeters is about a little more than 1,000th of an inch. And then if we go to the P6 value, we can go to the P. 6 is the type of thing that it is. So it's a 6 is an interference. So P for 60 to 80 millimeters is 0.032. So this is the maximum it can be over and above that. So that's essentially between 1/1000th and about 2.5 thousandths of an inch. I'll just do that calculation to see. So I've just calculated this, and the value that I'm getting is between 1/1000th and 2.5 thousandths of an inch. And that makes perfect sense, because when I measured the bore, sorry, not the bore, when I measured the outside of the axle tube, it was 2.501 inches, and it may have been a little bit more. It may have been 2.502 because when I was scraping off the paint, I may have taken off a bit too much material. But that, and assuming that the bore of the pumpkin is 2.500, which I don't know yet, but when I press them out, I'll find out. That 1/1000th of an inch sounds like exactly what I would have chosen if I was just guessing about what is the best for this kind of fit. So here, this is so using a book like this, you can basically see this is how the people who designed the axle shafts, the front axles, would have chosen their interference using this manual. Anyway, so that gives you an idea about how this is useful for you if you're working on your car. Get this book. If you have a good mathematical background, like you've done first year mathematics at university, you should have no problem understanding the mathematics in this textbook and being able to do all these calculations. The concepts may be a bit foreign to you, but you can basically become a mechanical engineer in full by reading through this book, this one book, and going through all the exercises. And then you basically be able to design almost anything. Thanks for watching.